Bojanic, and this summer I participated in the SROP program.
And I'm Uziel Mendez, and I participated in the SROP program. During the summer, we worked in the biotransport lab under the direction of Dr. Joe Bull here at Michigan.
And we worked on microfluidic droplet production for gas embolotherapy, which is a process we're going to go explain more about now as we enter the lab.
Gas embolotherapy is a developmental cancer therapy that uses focused ultrasound to vaporize PFC or perfluorocarbon droplets.
These vaporized droplets, or bubbles, can become lodged in blood vessels and occlude the blood flow to cancer tissue.
If the PFC droplet surrounds a second phase, such as a drug, this vaporization can be used to deliver the drug to a highly specific location, such as a tumor.
A problem with these droplets is that they're very hard to make, especially in sizes under 100 microns.
There are two current methods of making these droplets. One of them is amalgamation, which is high-speed shaken, and the second one is sonication, which uses ultrasound to make the droplets. The current problem with these methods is that the droplets formed have a very big size distribution.
If the droplets are too small, they won't be able to become lodged in the vessels, but if they're too large, they won't be able to make their way down to the capillaries.
Therefore, we are using microfluidic devices to narrow down the size of the droplets from 5 to 10 microns in diameter.
Our project this summer was to make dual-phase as well as monophase droplets using microfluidic devices, and now we're going to show you how we do that. The molds for our devices are made out of a polymer called PDMS. The first thing we do is mix the PDMS with a curing agent at a 10:1 ratio in order to give the molds the mechanical properties that we want. The mixed PDMS is then poured onto a silicon wafer that has the design for the microfluidic device engraved in it in order to make the mold. As you can see, the device has many bubbles, so we put it in a vacuum in order to remove them. Once we're done with removing the bubbles, we put it into the oven for about 4 hours in order to harden it. Once the PDMS is hardened, we cut out the PDMS and go to an off-site location to use a plasma oxidizer, which allows us to bond the PDMS with the individual device on it to a glass slide like this.
Once the device is complete, it is fitted with tubing which is connected to a syringe and then placed over a microscope. The syringe is then connected to a syringe pump which allows us to control the flow rates, and the microscope allows us to view droplet formation at a magnification of 10 or 4x. The microfluidic devices that we used incorporated cross junctions which use hydrodynamic focusing in order to create a Rayleigh instability to form droplets. You can imagine Rayleigh instability as what happens when your faucet is on a really slow flow rate, causing the water to drip and form droplets.
The fluids that we used for a single-phase droplet consisted of PFC in the center, surrounded by a bovine serum albumin solution, or BSA. We had to vary the concentration of BSA in order to find which one created droplets most effectively.
When making dual-phase droplets, an extra level of complexity was added. This was done by adding a second cross-junction down the microchannel.
Dual-phase droplets consisted of an oil or water core in order to incorporate hydrophobic or hydrophilic drugs. This is surrounded by PFC and again in the BSA solution. The challenge with dual-phase droplets was that the flow was extremely stable. This hindered droplet formation.
In order to get around this, we tried various different flow rates and flow rate ratios, but we found that adding surfactants to the fluids themselves had the best results.
We were able to make dual-phase droplets. However, the size distribution of these droplets is still relatively large. More work needs to be done with surfactants and flow rates in order to create monodispersed dual-phase droplets. We would like to thank Dr. Joel Bull and the grad students in our lab, Robinson Seda and David Lee, for continually helping us and supporting us throughout this project.
We would also like to thank the SURE and SROP program for allowing us to have this experience.